Hi everyone. Obviously I'm going to be sitting down for today. I did make it, but not with all my ligaments intact. That wasn't on the journey though, that was separate. So today I will be talking about three main topics. So there's going to be three kind of sections to this talk. Does mean there's going to be a lot packed in here, but I am here for the rest of the day today and also tomorrow and potentially on Friday. So feel free to come chat to me or email me or whatever if you have other questions. I have a feeling there's not many radio people here, just at least in the room, one radio person. Okay, that's good. I'm going to do a bit of a radio crash course, and I just wanted to make sure I wasn't going to go into details that everyone's very familiar with, so that's good to know. So I'll start off with a bit of my favorite science, which is Twinkling, Galaxies and baby AGN. I'll move into what I'm doing at the moment in my postdoc, which is a big survey in radio frequencies. And then I'll end on some of the work that I'm doing with the curriculum in Australia on gender representation. So getting started with the first section on Twinkling Galaxies. What are we looking at in radio? I want to mention if you are working on AGN but not in radio, I'm just going to call all AGN. Anything that we're really seeing in radio, AGN, everything. I'm not breaking into those billions of classifications that we see in optical, AGN, all AGN. Really what we need to know for AGN is that we have this central region here, that's the core of the jets, and that's really the actual central black hole that's accreting matter into the black hole, and that's really incredibly bright. We also see it as having a pretty flat radio spectrum, so across radio colors it's fairly consistent in its flux density, and so as we go to the higher frequencies, we're really dominated by the flux in that core and those jets. Whereas if we look at the lobes, these big extended structures, they have a power law spectra where they're really bright at the very low frequencies and they get fainter and fainter towards the higher frequencies. So we're really dominated by the lobes and the extended structure at the very low frequencies, and as you move to higher and higher frequencies, you're dominated by closer into the AGN. So the AGN itself, as I said, is accreting matter, and we see these big structures, sort of classical doubles or triples based on how many big clumps of bright stuff we see, essentially. Everything is quite broad strokes, obviously. We can go into a lot more detail over the different morphology, but this is really all you need to be knowing. The actual size of this AGN from end to end can vary drastically, but the largest ones that we see are about a few megaparsecs from end to end. So they can get well beyond the actual host galaxy themselves and be some of these incredibly large structures, and especially those big diffuse lobes, those big structures at the very low frequencies that we're sensitive to. Right, so AGN life cycles. I'm just going to twist myself a little bit more so I can see. There's three main phases of an AGN life cycle. Starting off on the very left, we have these really young, compact AGN. And when we look at their spectra, or how bright they are at all the different radio frequencies, they show what's called a peak spectrum. So this bright right in the middle, so if they get faint, bright, and then faint again. And we'll come into those in a little bit of more detail in a bit. We have the sort of main lifestyle, the main phase of typical AGN that shows this classic power law spectra at the very low frequencies, and really quite boring, straightforward. That is the vast majority of the AGN that you'll see in radio frequencies. And then we have the remnant phase, where the actual central supermassive black hole is switched off, so it's not actively ejecting any more energy into those lobes or jets, and so we see a steepening at the higher frequencies as those electrons are cooling off. So you can see from these different phases of the AGN, the spectra looks incredibly different, and we can start to tell what phase of life the AGN is in based on their spectral information. I said I'm going to focus a little bit on the peak spectrum ones. These are the ones I spent my PhD on, the ones I'm most interested in. So they're given that incredibly creative name because they have a peak in their spectrum, and they're about 5 to 10% of the population of AGN at radio frequencies. That number can vary quite a bit because, unfortunately, it's really hard to find them if you only have surveys at a single frequency. Then you're combining lots of different surveys taken at different times with different biases and different observational issues, and you need to have enough spectral coverage to be able to actually find that peak and identify it as a peak spectrum source. So 5 to 10%, but take that with a grain of salt as well. We still see the same typical morphology of AGN, so those double and triples, but they're just on far smaller scales, so on parsecs to kiloparsec scales rather than megaparsec scales of typical AGN. And the reason we see this peak largely debated, but ultimately there is absorption going on at those low frequencies that's causing that turnover. The cause of that absorption is what's interesting. We don't really know. Likely it's a combination of a whole range of things because the universe is complicated and it doesn't fit into nice boxes. But we can generally classify into two main categories, either synchrotron self-absorption, where the AGN is so compact, we're seeing it absorb its own electromagnetic radiation, the synchrotron radiation. And that's typically associated with the young scenario, that they're really compact and small because they haven't yet grown to the size of typical AGN. Otherwise, we see the frustrated scenario where these peak spectrum sources are compact, not because they're young, but because there's a cloud of dense material confining them and preventing them from growing. And in that case, we're seeing absorption due to free absorption from that cloud surrounding it. Probably there's a bit of all of that going on. So if you want a full review of that, there was a recent review that came out a couple of years ago that covers quite literally everything you'd want to know about peak spectrum sources. So go see that if you need it. So I've already hinted at the fact that the spectral information is really important at radio frequencies. It can help us identify what stage of life the AGN is at. But if we're looking even at peak spectrum sources in particular, we can also see the energetics of the AGN, the evolution. Maybe there's episodic periods of activity, and we can see those different periods of activity in the spectrum as well. We can get information on the environment from the absorption. But all of this information relies on having a really high quality spectra, having sampling across multiple frequencies that's really high quality. So yes, we can get all this information, but we need to have the data to do that. All right, let's look at radio variability. So there are two main categories: intrinsic or extrinsic. Intrinsic relating to the source itself, evolution going on within the source, versus extrinsic, as the light propagates towards us, there's some variability being caused there. So intrinsic, a couple of examples, it might actually be the source evolving itself. There may have been a sort of burst of activity from the central core, and we're seeing that propagate out into the lobes, and we can watch that evolution of the ejector. We can also see changes in optical depth from that cloud of free absorbing material. Versus extrinsic, we've got scintillation is the main thing, particularly at these radio frequencies. And I've put in bold there refractive and diffractive. Those are the ones that really matter at the frequencies that I'm concerned with. We're looking at low megahertz frequencies, and in particular, refractive scintillation is the big one. Diffractive is very much a concern if you're looking at pulsars, but anything else is far too big to show any diffractive scintillation. So for AGN, we don't have to worry about it, and it's really only refractive that's going to be an issue for AGN. Right. There it is in bold, just to say. The problem is, if you are showing intrinsic variability, that must mean that you are compact enough to also be showing extrinsic variability. So refractive scintillation also still has a requirement that it's compact objects compared to the scattering screen, so typically the interstellar medium. So if the AGN is a compact relative to that screen, we will see scintillation occurring. So if you're seeing intrinsic variability, the AGN itself must be very compact, and therefore we will also see scintillation. The inverse is not necessarily true. Something that's scintillating may not be evolving in an observable timescale for intrinsic variability, but if you're seeing intrinsic, you need to worry about extrinsic. Now, in order to differentiate between what's intrinsic variability and what's extrinsic variability, we're now limited by not only our spectral coverage, but also our temporal coverage. So once again, the spectra is incredibly important here, but now because it's variability, we also need the temporal coverage as well. So just to give an example of what this looks like, this is a really great paper by Laura Dreesen in 2022, looking at some meerkat observations. So they had incredible temporal coverage, and they also had spectral coverage. And if we look at, let's say, this one on the left here first, the top bin there, top plot is just the light curve, the raw light curve. The middle one is binned, so you can kind of see the variability a little clearer. And then the bottom one is the variability in the spectra, so changing in that spectral index and the spectral information. And you can see, yes, it's varying very much so in the light curve, but the spectral information, it's not really doing very much. There's just a lot of scatter. Whereas if we look at the one on the right here, yes, it's also varying quite dramatically in flux density in the light curve, but it's also varying in the spectral information. Now, if you are only looking at a single frequency in that light curve, you would miss this information entirely, and that can really be the key thing to identifying what's causing the variability. So what has low frequency variability done to date? We have been really limited by the data that's been available. So a lot of the observational constraints mean that surveys are limited to a single frequency, to small population sizes, or to the higher frequencies where it's been easier to detect short timescale variability. The megahertz timescales of variability is not really great for example, a PhD length time, because often you see things varying on timescales of years. So you kind of put all your eggs in one bucket, definitely not speaking from personal experience. So if we look at this plot in particular, there's one key thing I want to point out, and that's this region here of the plot. So this is a peak spectrum source from Tingay's paper in 2015. And the key thing that's interesting here is that the different models in those epochs really start to diverge dramatically at the low frequencies. At the high frequencies, they look fairly similar, but the low frequencies is really where all the juicy good stuff is. So that's where we need to be spending a lot of our energy, but a lot of the low frequency surveys, we don't have the temporal coverage. We've basically just got to the point where we've covered the sky in radio frequencies, and we're only just starting to get the full sky coverage with multiple epochs. So this is really a new space observationally. So what did I do in my PhD? I had a look at spectral and temporal observations. So I looked using GLEAM, the Galactic and Extragalactic All-Sky MWA survey, which is this lovely radio color image here of the Milky Way. It is one of the largest spectral variability surveys to date because it covered such a wide area of the sky. So the MWA has a huge field of view, which means that we can survey the sky quite rapidly. And GLEAM covered the entire sky and then kind of went back to dabble in a few areas as well. So the South Galactic pole region covered about 5,000 square degrees, which meant over 20,000 sources. That is a huge population to be doing variability analysis with. And above that, we had 20 individual flux density measurements. So, frequency measurements. So now we have temporal and spectral coverage, which is really what's interesting. The main problem is that this is a new parameter space, so the statistics to be able to say this is variable, this isn't, and this is how it's variable was quite challenging. And I think it's only going to become more of an issue as we head into more big surveys, SKA era and ASCAP era. It's really going to be quite an issue. What did we find though? There are a lot of things doing a lot of things. At the time, we actually thought there wasn't going to be pretty much anything. This is megahertz frequencies. We're looking at those big extended structures, those lobes that can be kiloparsecs in size, if not megaparsecs in size. Things shouldn't be doing too much on the timescale of about a year. That was not the case at all. So we saw peak spectrum sources that seem to lose their peak spectrum and flatten in the space of a year. We saw things get brighter. The following year, we saw things that were peaked again flatten. We saw things like this that were just chaos. Does anyone know what that last one is? It's a pretty famous source, no? This one is the only one I was very confident I knew what was happening, even though it was the most chaotic. This is a well-known pulsar. So this is actually diffractive scintillation that's going on here. That's why we don't see a smooth spectrum, because the mosaics in GLEAM are combined observations over a night and then multiple nights added together. And so essentially in your pulse spectrum and the diffractive scintillation, you're pretty much randomly sampling unless you take care to measure a pulsar spectrum. And so if you don't do that, you end up with something like this. So this is the diffractive scintillation going on. And so solved for at least one of the 20,000 sources or so. So when we looked at this survey, as I said, there was over 20,000 sources, and we found hundreds of them were variable. And not just that they were variable, but there were 51 that were dramatically changing their shape in this period of just 1 year. Now, scintillation, in particular refractive scintillation, cannot explain a change in spectral shape at megahertz frequencies, and certainly not in this period of a year. So to see 50 of these sources, which may not seem like a lot in 20,000, but it's actually very many to see 50 changing their shape in just 1 year. We really had to think about what's going on in the physics. These sources are far too large to be showing such a dramatic change in their spectral energy distribution in just 1 year. But most excitingly, we saw that peak spectrum sources are particularly variable. They're a population that are showing far more variability than typical AGM. So very exciting. All right, so what's actually going on? Well, we needed more data, as always. So now, not just with the MWA, we combine the ICRAR as well to get some higher frequency. As I said, temporal and spectral coverage. That's really what we need. So we increased our spectral coverage, but we also increased our temporal coverage. In theory. Unfortunately, as any observers in the room might know, scheduling doesn't always go to plan. So we did only have, in the end, 2 epochs that were simultaneous between the MWA and ICRAR, but the MWA had incredibly high time sampling of months to years, which was really fantastic as well. And what do we find? There are a lot like this, where we see at the megahertz frequencies, they're fairly constant in shape, but they're definitely getting brighter and dimmer throughout the year. The higher frequencies, there wasn't actually that much going on that was significant, not across the year. We also saw ones like this, where again, at the megahertz frequencies, let's just zoom in there, it gets really exciting. There's a lot going on, it's changing its shape, and in fact, it's changing its shape from July to September. So we were already freaked out that things were changing its shape on a period of a year, and now we're seeing they're changing their shape on the period of a couple of months. So really, our understanding of how fast these things can be changing was way off. They're doing some pretty cool stuff a lot faster than we anticipated. And the cool thing here is we can measure the actual peak frequency. So where its peak is in each of those observations, that's one of the great benefits of the MWA and GLEAM in particular, that it samples such a broad range of frequencies, it has such a great spectral coverage that we can actually measure that curvature within the band of MWA. And seeing this peak frequency, particularly in that last epoch, go to higher frequencies is weird. To see the evolution of an ejector, so if an AGN is bursting something out and we watch it expand and cool as it ages, we should expect that peak frequency to shift to lower frequencies. So we're seeing it age in reverse here, which is very odd and not really what we anticipated. Thankfully, with some more observations at the higher frequencies, we can also see that it's not scintillating at the timescales we expect for the higher frequencies, so it's not doing anything on periods of hours at high frequencies compared to, I've got another example there you can see in the purple. That one is doing something at the higher frequencies. That is showing the scintillation, suggesting it is incredibly compact, or it has a really bright compact feature. So this other one that's showing dramatic changes at MWA is doing absolutely nothing at those higher frequencies. It's quite a boring source in other circumstances. So the megahertz is really where it's the most interesting. And actually, because of this sort of confirmation, we're able to say that this is due to a variable opacity. It's really changing that absorption mechanism, which means there is a really clumpy dynamic environment around this AGN, and we're seeing these clumps move into and out of the field of view on really rapid timescales for megahertz frequencies. So this was incredibly exciting to have found, because now we have an example that this source, this peak spectrum source, we know confidently what the variability is because of the spectral information, but more importantly, we also know what the absorption mechanism is, which has been incredibly hard to narrow down for peak spectrum sources. So hopefully this can help us with understanding the peak spectrum evolution. Right, so a bit of a summary of this first part. There was a bit of a whirlwind of science. So firstly, peak spectrum sources and AGN in general are super cool and interesting, and you should love them. Megahertz is where all the juicy good stuff is, especially for variability. And spectral information is the most vital part of that. To be able to differentiate what's going on in the radio variability, we need that spectral information. So before I move on, are there any questions on this part one of the talk?
Could you, sorry, you might have explained, but could you explain again why scintillation doesn't change the shape of the spectrum?
Yeah, sure. So it doesn't change the shape of the spectrum at megahertz frequencies and across the MWA bandwidth. So it can change the shape, but it is quite a broad bandwidth that it changes. So across MWA, it shouldn't be making any change. We're talking, it should be over the range of hundreds of megahertz, not just the 200 or so that we have. It should be many hundreds. And so we did do a look saying, is it actually that we've misjudged that? And maybe it is more of a narrowband effect than we thought. But as far as we could tell, no. There is a lot of hand waving in scintillation calculations, but we're fairly confident on that one. Yes. No worries. Other question? Yeah?
I just ask sort of very broadly, how big is the emitting region for standard AGN, just in terms of sort of light crossing times?
Millions of light years for a typical AGN. Yeah, you're looking at 3 million from lobe to lobe. but the core part, which is what's showing sort of rapid variability, can be on the order of a few light years, depending on what frequency you're looking at and what sort of part you're probing, and also what type of AGN it is. Yeah. But also at these radio frequencies in the lobes, yes, they're these big diffuse extended structures, but they can have hotspots as well. And those hotspots can be incredibly compact. And while they might not vary intrinsically on short timescales, they can dominate the flux at the low frequencies and then show scintillation, whereas the big diffuse structure wouldn't, but the hotspot can. Yeah. Any other questions? Cool. All right. So part 2. This is what I'm getting onto now. So this project, the first part of my project, really came about from GLEAM, that survey that covered the entire southern sky, wonderful spectral coverage with the MWA, absolutely love it, and a big fan because my entire PhD came out of it. But now the MWA got a big upgrade, and so GLEAM's getting a big upgrade as well, and that's where I'm at the moment. So let's do a bit of a GLEAM versus GLEAM-X. GLEAM covered the entire southern sky south of +30 and a spectral coverage from 70 to 230 megahertz with 20 individual flux density measurements in there, so subband measurements. It had a mean RMS of about 10 millijanskis per beam, so it's quite shallow for radio. I realize that Janskis per beam is probably a unit many people aren't familiar with, but that's quite shallow in radio terms. And we've got 100 or so arc-second resolution, about 2 arc minutes, and gets worse at the lower frequencies. So it's really not very high resolution, which can make it hard even comparing to other radio surveys. Incoming, GLEAM-X, kablamo. Imagine hot sound effects coming in with this. So we're covering the same sky region, so everything south of +30, but in the second data release, which is what I'll focus on in this talk, we're covering the South Galactic pole region, so from about 20 hours to 6 hours, and so it's about 9,000 square degrees. It will obviously then expand to the rest of the sky, but at the moment, just that South Galactic pole region. It's covering the same frequency coverage as GLEAM, so it's directly comparable in that sense. But we are over an order of magnitude better in sensitivity than we were with GLEAM. So on average, we're about 0.8 millijanskis per beam RMS, which is way better than we expected, which is fantastic. And you can see there's a huge improvement in the resolution as well. So we're about 45 arc-second resolution, which is awesome. Right. So in particular, the data release 2, we have 3 main tranches of observations that were taken, sort of chunks of the sky, and we focus on a single drift scan. So we're looking at a single declination and watch as the sky sort of drifts over, and then we combine that into a single mosaic for that night. And each night we then mosaic together to get the entire mosaic of everything. So in data release 2, we've got the 7 deck strips and covering just that region in the middle there that I've shaded in the dark pink. And so those are observations that were taken from around September to October in 2020. Overall, the entire survey has got 2 petabytes of raw data. I don't even want to get into the very many more intermediary data products and final data products, and that number really escalates. We're also doing instrumental, full instrumental Stokes polarization and RM synthesis. I'm not going to talk any more on that because I have no understanding of polarization, but I know that we do it, and people who do want to do polarization can use it in some way that they may understand that I don't. So what do we have? It's a catalogue of around 650,000 sources. To put that into perspective, the entire GLEAM survey, which remember that is almost over 3 times the sky coverage of data release 2, it has 300,000 sources. So just in a third of the sky, we're already more than double what GLEAM had. Of those, we've got 550,000 that are spectrally fit. So I've mentioned many times that the spectral information at radio frequencies is the most vital part. That is incredibly important. So to have 550 sources that have spectral information, and of those, about 20,000 showing a curve in their spectrum or showing a peak spectrum within the MWA band is so exciting. At the moment, there is a big catalogue of peak spectrum sources that's about 1,500. So we might be increasing the population of peak spectrum sources by at least an order of magnitude, it looks here. So that's amazing. I've got this image down the bottom here. This is a comparison between GLEAM and GLEAM-X. You can see the increase in resolution, a decrease in the noise, but the diffuse structure, particularly on the right of the screen, also fades away as we sort of fade into the gleam. Same with that sort of big bright galaxy in the middle there. You can see we become less sensitive to that big diffuse structure. And that comes with the higher resolution and longer baselines in phase 2 of MWA, which is a shame because that big diffuse structure is really interesting. So we don't want to be losing that, but we want the higher resolution. So what do we do here? Well, we can combine both GLEAM and GLEAM-X to create this image on the very right here, where we get the sensitivity of the diffuse structure from GLEAM with the resolution from GLEAM-X and create this high resolution, but also diffuse sensitive image on the right. So that's using joint deconvolution and IDG, image domain gridding. And this is actually all done with just 2 minutes of observations on the two-minute observations. So 4 minutes of data has gone into that image of the galactic plane, or that region of the galactic plane. And that is just at one frequency as well. This is work that's being done by a PhD student over at Curtin as well. And so we'll be doing a full IDG joint deconvolution of GLEAM and GLEAM-X for the galactic plane, and that'll be coming in a future data release. So it's going to look just absolutely amazing. I can't wait. There are some features that we've come across in this processing. With any big survey, there's always going to be some fun features. For anyone who has processed radio data, side lobes are a nightmare, but unfortunately with the MWA, side lobes are a humongous nightmare. If we're pointing low on the horizon on one side, we're actually even more sensitive to the sky on the complete opposite side, which is incredibly unfortunate if you're interested over there and not here. And as a result, what we can see is essentially an alias of sources that are in this side lobe, not in the area that we're pointing, but they can pop up in our image because we're so sensitive to that other area of the sky. And that's what we're seeing here. You might not be able to see it, so I've highlighted, there's actually this repeating splodge that goes across the screen. And that's that drift scan as the sky moves across. That bright source was still in our side lobe each time. And so it got aliased into each of those 2-minute observations. And we see that splodge coming up. That is incredibly annoying. But we have started to deal with that using a side lobe subtraction and a self-calibration as well. So some pretty complex data reduction going into this pipeline as well. We're also seeing the ionosphere. We're heading into a solar maximum, which might be fun for some people. It is an absolute nightmare in megahertz frequencies. This is just a GIF here where we can see the source positions shifting from where we expect them versus where the ionosphere has placed them from our perspective. And that's just over a couple of 2-minute observations. And we try and create a sort of map of where the sources are moving and adjust for that. But as we're heading into this solar maximum, the ionosphere is just a nightmare, and it can mean that calibrating your telescope entirely is a nightmare and almost not possible. We're actually working with a group in the US, the Naval Research Lab, who is very interested in measuring the ionosphere, one man's trash, another man's treasure. They're very interested in characterizing what the ionosphere is doing using the data we're producing here. So this is entirely separate, just we're using it to find the bad bits and get rid of them, and they're taking all the bad bits and finding their good bits, I guess. So we've actually submitted a paper measuring turbulent ionospheric disturbances, or TIDS, and they can actually measure this quite well. So it's a really interesting paper that I won't say I know much about. So, as I said, in this data, what's available, what can you get your little hands on? There is a catalogue of about 650,000 sources, and doing some cosmology. Again, another PhD student at Curtin is using GLEAM and GLEAM-X, just GLEAM-X to do a cosmology. I am not a cosmology person either. I won't pretend to understand what this plot is, but I was told by Brandon that it means we're all in the same universe and everything is consistent, which is great. I can't tell you anything more than that, but GLEAM-X is behaving as we would hope it would, so that's great. What else is available? We have image cutouts for all the mosaics that we're producing. That will be hosted on Data Central. At the moment, the first data release, which was just a small region to sort of test the pipeline, that's already on Data Central, and the following data release 2 mosaics will be there, as well as subsequent data releases too. There is per night mosaics and catalogues. I've got a star next to it. We're not likely to be hosting that anywhere because the data volume is just huge, but I do have access to them. If it is something you're interested in, let me know. We can absolutely sort something out because there's a lot of really interesting data that can be found here. And then intermediate products, I already showed an example of the binocular imaging there, which is how we're measuring the ionosphere and those TIDs. But we're also doing transient imaging to try and find more long period transients, like the one found by Hurley Walker a few years ago. And I'll be looking at weekly variability from those drift scans from night to night in the observations of GLEAM-X. I've got question marks there because if there's other things that you're interested in, we can almost certainly add this to the pipeline as a default thing in the processing and give you these data products, you know, free. So yeah, let me know if there's something where you're like, this is really cool and I would love to have it. We can absolutely see if there's a possibility to sneak it in there. Early results, obviously I'm interested in spectral variability and peak spectrum sources. These are a couple of ones that I think show some pretty interesting stuff. The one on the top right there, the blue and the purple, the observations from that big survey from GLEAM. You can see it's sort of kept its same shape, but just shifted up and down, very typical of scintillation. But now when we look at GLEAM-X about 10 years later, we see that the peak has shifted to those lower frequencies and it looks like that source is actually evolving. Now over the 6 years timescale, that's believable for these peak spectrum sources to see this as genuine evolution, but that's incredibly exciting to actually see that effect and has not really been done to a large scale because of the constraints and observations to be able to observe this kind of effect. We're also seeing sources on the left there, which seem to have a fairly constant peak, but maybe changes in the optical depth again, so changes just in that absorbed part of the spectrum. And another very interesting one, this one here, is recently a paper that came out for this one saying they think it is a restarted AGN, and so it switched off for quite a while, and now it's come back on recently, and the orientation of the AGN has shifted to be more blazar-like, so pointing sort of right down the barrel of the gun towards us. I've got an image of the cutout in GLEAM there. You can see there's an isolated core, and then those lobes on either side. And if we look at the variability from this one, I originally just looked at the variability in my catalogue from the first survey and I was like, it's not variable at all, it's not doing anything. But as soon as you add GLEAM-X into this, in the pink, it starts to get very exciting. I don't fully know what's going on here, but I'm excited to find out. It's cool. So some fun early science. Cool, all right. Any comments on that part of the seminar before we move on? Yes?
Does GLEAM or GLEAM-X, I guess, does that contain sort of more nearby sources, or is it really mainly focused on galaxies? Is it like avoiding foreground source?
So this data release, it was purely extragalactic in that South Galactic pole region. So we're not really sensitive to things closer, and there's not many there to see. But in the galactic plane, we'll be doing releasing that as well. So supernova remnants are really where GLEAM shines as well. And that's part of the reason, that's the work the PhD student is doing. That's why she's doing the joint deconvolution as well. So we will be releasing more nearby things. Galaxy, I don't know how nearby you mean. Yeah, in our galaxy. So I talk about my low redshift sources that are like 2, and it horrifies my friends. So in the galaxy, yes, we'll be doing a data release of the galactic plane as well, and that will have sources there as well. The low long period transients are obviously galactic as well, so that's part of the reason we're doing that search as well. We don't expect to find many of them, obviously, in the extragalactic region. Hopefully it'll be more exciting in the galactic plane, but yes, it will be there, yeah. Any other questions? No? All right, so this last section is kind of a full flip in a very different direction, and is work that I was doing. It actually started prior to my PhD, and it's still going now that I finished my PhD, which I think shows the speed of bureaucracy. And this is also work that was done by Shanika, who used to be here, but has now moved off to France. Anyway, so it does mean that I can now say we're international, baby. It's very exciting. So we're a group of about 12 volunteers. Most of us are astronomers, and most of us are also ECRs or students, or were students when we started but have now graduated. You can see we're all over Australia, and now, yeah, internationally in France as well. And I do want to mention that this was a big collaboration. This is group work done by a team of us. I've put in bold there names of people in astronomy. I will say there is another Tegan Clark in astronomy. It's not that Tegan Clark. I feel like someone got angry at me being like, you didn't put Tegan in bold. I'm like, it's a different Tegan. Oh, thank you. but I haven't not bolded you out of disrespect or anything, just so we're all aware. But as I said, this is a big team effort, a big group of us, not just astronomers, there's also education experts, environmental experts, and there is also my sister, who is also a scientist, but there is, you know, a bit of, what's the word, nepotism, is that it? So my sister joined as well. So who is IncludeHer? What are we doing? This was founded back in 2018 in New South Wales. At the time I was actually working in physics education research, and we were doing work to help train teachers for an incoming physics syllabus. There was a lot of new content, a lot of new formulas, and most physics teachers in New South Wales are not actually physicists. So that's kind of scary if you have no training in physics. So it was our job to help train them in this incoming syllabus. It was actually as part of this that someone pointed out Marie Curie wasn't mentioned in radioactivity, and that seems like just a touch of an oversight. And so thus began IncludeHer. And IncludeHer really started with the aim to change the way that we're presenting science to students, to change the representation of STEM in high schools. And it's really grown to a national campaign, as I showed. We're a whole team of people around Australia and France. And that is largely in part to a talk that I gave here in the height of lockdown to the Women in Physics group here, and then I think also to the rest of the department, largely also organised by Shanika, where I was kind of just doing this as a hobby on the side, and Shanika was the one that was like, no, everyone needs to know about this. And we did a lot of talks around Australia, and because it was COVID, because we were all in lockdown, everyone was looking for talks because no one could travel anywhere, and I could then give talks to a whole range of places virtually, which is incredibly exciting. And I think we're now heading sort of out of COVID, if that's even a thing, and there's this push to go back into person seminars, I say, as I travel over here to give a seminar in person. But I think we shouldn't underestimate the value of these online seminars. IncludeHer really probably wouldn't be where it is today without those online seminars. So I want to take a moment to appreciate that as well. Right. You've had a crash course in radio. I'm going to try and do a crash course in education and gender research as well. There is a huge amount of research out there. It is a massive field that I think is not really known even by teachers and education people, just the amount of research that's out there in education research. And in particular, gender research as well. There is a lot of research showing just how big the issue is, how complicated the issue is. And I think we can sort of all agree that yes, representation and women struggle in STEM. There is definitely an issue there, but seeing the stats and seeing the research behind it can also be quite jarring, I think. So the STEM Equity Monitor from 2022, and there's also been updates, I think sort of every year they give updates, is really showing that women are underpaid, they're underrepresented, they're underappreciated in practically all STEM fields and at each level, and it gets worse and worse at the higher levels. We're also seeing decreasing numbers of students enrolling in STEM subjects from 2018. There is, if you go on the Women in STEM Ambassador page, they have an interactive data module thing where you can select different courses, different stages, the enrollment numbers. And if you look at the raw numbers, it looks like we're actually increasing the representation of women enrolling in science subjects. But if you break that down by subject, that comes down exclusively to environmental science. We're not seeing that same effect in mathematics. We're not seeing that same effect in physics in particular. Biology and chemistry are fairly constant. They're not decreasing, but the increases that are being reported are not actually universal across STEM subjects. So yes, I think it's worth appreciating, but we need to look at a deeper level what's actually going on, because we can't just gloss over this as one big issue. It's really complicated with a lot going on. And so we're not seeing the effects where there are so many programs out there, and we're not seeing those effects come through in the enrollment numbers and the representation of women in STEM careers. Gender and STEM generally in high school, if we hone in just on the high school ages, there is some core concepts related to education and research. Self-efficacy, essentially a student's ability to judge where they're at relative to their peers. It's also related to their resilience, should they get something like a bad mark or a bad comment, their resilience to that going forward and staying in the course. And so women are often experiencing lower levels of self-efficacy, they're reporting lower levels of resilience to these bad marks, and that can have detrimental effects on their progression through a science career. Interactions with teachers, this was a really interesting paper that came out just this year. Even the perceived negative interaction from a teacher can detrimentally affect the confidence of women in high school courses. So even if their teacher isn't actively saying negative things to that student, if the student feels that the teacher isn't appreciating them or responding positively to them, we still see an impact on their grades within their science courses. Stereotypes and stereotype threats. If there is the perception that someone like you is not good at science, you are vulnerable to performing worse because of that stereotype, particularly if you're asked to mention that at the beginning of an exam. So if you're putting there being like, yes, I am an Aboriginal or Torres Strait Islander person, yes, I am a woman, now go on and do this exam on a topic that is typically associated with people not like you, and people like you are in fact often very bad at this. We can see an impact on the grades as a result. Role models and access to role models, or I should say lack of role models also. So there's a lot of research coming out about the impact of role models, but in particular, the type of role models. So not just having role models around, but they have to be relatable and authentic role models. Just having random women around isn't necessarily going to solve the problem, particularly if they're all Nobel Prize winners, because let's face it, if you're in high school, you don't really relate to a Nobel Prize winner. That's quite a high achievement. I barely relate to a Nobel Prize winner. So we need relatable and authentic role models at each stage of education, not just at high school, not just at university, but every stage of instruction. And then lastly, belonging. This is really the sort of up and coming term that we're seeing that incorporates all of these things. Because realistically, this is a very complex problem that incorporates pretty much all of these. They're interacting. It's a very complicated thing. Belonging is kind of the increasing term that's being used to describe the interaction of all of these things. So if a student has a sense of belonging, they have a role model they can relate to, they don't suffer from this stereotype threat because they feel like they belong here, we can see the positive impact that's happening on their progression and on their grades as well. But inversely, if there is no sense of belonging, if even one of these sorts of things is failing, we can see that effect as well. So belonging is really the big thing, and we want to be increasing that sense of belonging to increase the progression and engagement with STEM. Right, so what is IncludeHer doing? How does our research fit into this? So we're currently working with curriculum developers in Queensland. I've got there in brackets and New South Wales. This started in New South Wales and I've been trying to work with New South Wales since. We're yet to see any changes actually implemented in New South Wales. And so I have them in brackets. As I mentioned, bureaucracy is long and slow. But Queensland has been really, really receptive. They're actually giving us their draft syllabus for revision and comments, and we're working pretty closely with them to help devise a new way of teaching the content. It's been really interesting to see. A lot of them started off saying this is just too big of a problem. We just want to update our curriculum and not really do anything more. And then seeing people who are yes, familiar with the content, but now being tasked with, okay, I have to find modern examples that are actually interesting and not just a pale male stale, let's put something fun here. And you can actually see them get on board and start to engage with the content as well. And I think it's probably going to be pretty easy to say if a teacher is engaged, if your curriculum developer is engaged in this content, it's very easy to make the student also engaged. If a teacher is enjoying what they're teaching, students also enjoy engaging with that content. We also have conducted a full curriculum analysis. So we've done a content review of main courses in all states and territories in Australia. So that's biology, chemistry, environmental science, and physics. Those are the 4 core subjects that all states cover, not that they're exclusive, that there are no other science subjects. States do have other science subjects, but not necessarily the same ones in every state. And also these are the ones with the highest enrolment numbers. Particularly environmental science has skyrocketed in the last few years. I'm going to come back to that in a bit as well. All right, so what was our research? We went through every single mention of a scientist in all of those courses for each state and territory, and we classified it as either a concept mention or a scientist mention. So a concept mention is where the scientist is not really the focus here. It's something that's named after a scientist, so it's sort of an incidental mention. So for example, the Stefan Boltzmann law or the Doppler effect. You're not really talking of Doppler there. We're talking of the effect, but it's named after that scientist. Alternatively, the scientist mention is where the scientist is actually the intended focus of that sentence. So the scientist is really what we're trying to focus on here, or it's a completely unnecessary mention. So I sort of just added in there for no real purpose, other than to be like, a scientist. So another example, this is taken from the WA physics curriculum. Here we've got Thomas Young showed through experimentation, blah, 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 blah. That's clearly relating to Thomas Young, the person. Yes, we're looking at the content of the science that Thomas Young has done, but there is a very clear focus that that science was done by Thomas Young, and let's mention that Thomas Young is the scientist that we're learning of. So those are the two classifications. And then we broke down those mentions of scientists according to gender. And I want to take a moment here. Everyone take a moment to look at that. I myself don't identify in a binary. Yes, we've classified in binary. That is more from a lack of data, not from a lack of existence. All right. It's out now, finally. Very, very exciting. It came out a few months ago. After some hassles relating to Word versus LaTeX formatting with the Education Journal. It has been quite an experience publishing with an education journal. Lessons have been learned, but it's finally out and you can access it. It is open access as well, but obviously you can come to me if you want a copy of it as well. Cool. So let's go into it. Let's have a look at all the mentions and break down the stats. So we found there were about 450 mentions of concepts or scientist concept mentions versus about 130 mentions of the scientist themselves. So we're overwhelmingly seeing the mentions being included because of these concepts rather than a focus on the scientist, but there is still quite a large number of scientist mentions. Overall, there are 144 unique scientists that are mentioned. That's the gender breakdown. Now, I don't know if there's any Parks and Recs fans in the audience. Yeah. So yes, those dark purple slivers in Queensland, South Australia and Northern Territory, those are the women that are mentioned. It is pretty heartbreaking. All right, let's break it down further. So we find, as I said, mostly we're mentioning scientists because of naming conventions, not necessarily a focus on the scientist. But that is quite outdated science. We're seeing quite old science from hundreds of years ago. We're promoting this lone male genius narrative because it's always this sort of individual person, maybe a pair of people working together, but we're not seeing teams, collaborations. That's not really anywhere to be seen. The approach to teaching across Australia seems very chronological. So we learn topics as we discovered them. That is a very criticised pedagogy. It's not engaging for students. It's not really useful in a modern scientific world. And it doesn't really tell you how the science actually applies in life, which is far more exciting and far more useful whether or not you actually go on to further scientific study. So that pedagogy is highly criticised, so it's already outdated, as well as the people we're teaching being outdated. And because we're teaching this lone male genius narrative and the chronological pedagogy, that is actively going to ignore minorities who have historically been excluded from these formal recognition and formal institutions. So to have a pedagogy that is already not a good pedagogy, that then we know will actively ignore minorities, there's a lot that needs to be fixed in this curriculum. I also want to take a moment, let's have a look at the geographic breakdown here. There is one pretty clear absence. Not a single Australian was mentioned across the entire Australian curriculum, not one Australian. It is almost entirely from European countries and the US. And that is pretty upsetting. I think we can all understand that we see a lot of people moving from Australia to study abroad or to do their first postdoc abroad because there's this inherent narrative in the way we're teaching science that Australia is not the forefront. Australia is not where science is happening. If you want to be amazing at science, if you want to be at the forefront, you need to leave Australia to do that. And that's reflected in this curriculum. I know in WA as well, we have a similar problem, but of people migrating from WA to the East Coast and then the East Coast abroad. And so we need to be starting to appreciate the local science that's going on here in Australia and showing that we are innovative. We do have incredible science here because our students are not getting that message. All right, break it down even further. This is a complicated big plot. Don't worry too much. I'm going to talk about the bits I want to highlight. Firstly, there seems to be two approaches in states and territories. We've got content versus context approaches. So ones like South Australia, sorry, not South Australia, ACT and Victoria take a very concept approach. So there's not really mentions of scientists themselves. There's not really mentions of anything in the historical sense. We're really only mentioning because it's named after that person, we have to. ACT doesn't have a single mention of a scientist. It is only concept mentions, and Victoria is really not far behind. Other states, like South Australia and New South Wales in particular, have a really clear focus on mentioning the concept, the scientist. There's a really big value on scientists and the work that the scientist has done, but it's only men that are mentioned. And so, yes, we value the scientist, but only if you fit this very narrow idea of what a scientist is. Physics versus environmental science. So consistently for every single state and territory, physics recorded the largest number of mentions, whether it was concept or scientist, but the largest number of mentions, versus environmental science, which consistently had the lowest number of mentions of any subject. Now, historically, and when we look at these masculine versus feminine sciences, physics is seen as this masculine science. It's seen as a male-dominated science. It's seen as very technical, very mathematical, and that is also reflected in the syllabus. We see the appreciation that men have contributed to physics, that it is the height of importance, and physics is sort of this put on a pedestal. Einstein, we can't touch Einstein, he was perfect in every way. All the science he did was incredible. And so we see all these mentions reflected in the physics curriculum as well. Environmental science, the pioneers were women. Women have been fundamental to environmental science, and it's quite a modern science. And so that's not really being shown in the curriculum because we're not appreciating the work that women have done, and we're not seeing that a value of scientific work by scientists by the mentions of environmental science. It's just sort of spontaneous knowledge that appeared suddenly, and we'll just learn this content. And so I think the perception of physics versus the perception of environmental science, it is interesting to see that if it's seen as a male science, we have a lot of mentions of male scientists, but if it's seen as a women's science, there's not many mentions. And then we also see that reflected. Biology also has very few mentions as well. So, as I mentioned, they all follow the same sort of pedagogy of this chronological order, which is highly criticised and very discovery focused. So it's sort of presenting this idea that science is done by isolated individual events of discovery rather than continual progress and continual growth, which is not really helpful, particularly at high school, when we're trying to teach students what does science look like. If you're interested in science, here's how you be a scientist, here's what science is, what's involved. If you're being taught that science is only done by these isolated big discoveries, at single points in time, you're looking at that being like, well, I don't feel like a genius, I don't feel like I'm going to make a big discovery. Science clearly isn't for me. But working as part of a team, constantly finding new things, always learning, that is a far more accurate representation of science and far more welcoming and engaging to people who don't fit that really narrow definition. And lastly there, I've got Aboriginal and Torres Strait Islander science. Good luck, basically. There's a mention in almost every single curriculum, a paragraph right at the beginning of the syllabus that says, you should teach Aboriginal and Torres Strait Islander science, it's very important, and then zero help with how to do that. There is no actual mention of how to do that. There are no dot points of that other than a few in environmental science, but otherwise it's up onto the teachers to be able to do that. Indigenous knowledge is really just not there at all. But we appreciate it, we want it there. So that's really not helpful at all. Teachers have enough on their plate. They don't need to be doing the extra work. So, this paper came out, as I said, a few months ago, a month, I don't know, it's been a while. It came out recently, and we did a big media push related to that. And I talked about environmental science being this perception of a woman's science and the undervaluing of the work that women do. I think these comments also highlight that. What was it? Which one was my favourite? I've got to find it now. Useless ideological floundering after reading the paper. Feminist blarney. A parody account. That's a fun one, given this is the only real TikTok I did on this paper. The rest of it is about my astrophysics research. So not a parody account about social science as well. I do astrophysics. Anyway, the response to this paper has really highlighted that this sort of work, the education research, gender research, women saying that there is a problem is undervalued. Work of women is undervalued while the work of men is appreciated. I think a really great example that highlights this, first of all, we've got the Tillies recently, which is also why I'm croaky today. I went to the game on Sunday. It was amazing. A lot of goals to cheer. No voice left. But the work of the Tillies, they've really shifted that narrative, because before, the Socceroos, that was it. That's all we care about. And now Tillies, everyone's on board with them, which I love. Another example, when you talk about cooking, we think of women as being the ones in the kitchen at home doing the unpaid labour of cooking for the family, whereas all the top chefs in the world are men, and men dominate professional cooking in that environment. So if work is being done by men, let's pay them well, let's appreciate it, let's give them the work, the validation they need. But if women are doing the work, you should be doing that free. It's undervalued. There's no appreciation. You should be doing that from the goodness of your heart. And that's reflected also in this work that we've done out of the goodness of our hearts as a hobby, because we care about it. And the response is mix match. Right. So summary of this section, Australian science education is really outdated, and it absolutely needs to come into the 21st century. Even just the 20th century would be nice. There is a narrative that's present in all courses across all states that is particularly harmful for women and minorities, that we're seeing at such a critical stage in their career when they're deciding what to do, whether to pursue a career in STEM, and we're telling them this narrative is really quite a problem. Thankfully, IncludeHer is working to fix it. So we're working with curriculum developers, as I said, and in fact, tomorrow I'm even having a meeting with the Australian curriculum developers to see if we can change it Australia-wide, and so the states have to follow. But we're also developing an in-school program that will work with both teachers and students, helping the teachers to adapt their current lesson plans so they can include a more diverse representation. But we want to be able to produce sort of everything for them. Teachers don't need the extra work, so if we can do it for them so that it's easy to implement, that's the goal, as well as showing students sort of examples of scientists at every stage, not just the Nobel Prize winners, but examples of scientists local and ones they can relate to as well. Even if it's, you know, undergrad students that have come from their school, where they can see immediately the next step from high school into university. If you're interested, get in touch. There's an email there. Obviously, I'm around. You can also just talk to me, or you can email my personal email as well. All of that is fine. But more information or questions there if you want. Cool. Thank you.
Did you look at maths as well?
We had a brief look at it. It's taught very different to science in terms of the syllabus documents. If we were going to do an analysis of the sort of gender representation there, this is a study that has already been done as well, so I don't know how much it would help, but more of an impact is the fact that all the examples, for example in finance, if you make poor financial decisions, you're a woman. If you make good financial decisions, you're a man. So maths has a very different problem when teaching. Yeah. Yes?
Yeah. Honestly, name and shame the commenters. But
Yeah.
anyway, great talk, really enjoyed it. But my actual question was, does environmental science also do the chronological kind of approach as well?
Not as much, but yes, still to some extent. But being a more modern curriculum and a more modern topic, like I think it was only introduced maybe in the last decade or so in some states. And because of that, it doesn't have quite the same approach that the other ones have of just like, this is the way we've always taught it, so this is the way we'll do it. So they kind of had to start from scratch there. So yes, but not nearly to the same extent that the other courses do. Yeah. Which is also why there's more Aboriginal science in the environmental science stuff as well, because there's more of an application of, I mean, it's upsetting because most of the time it's like, look at how we've destroyed this Aboriginal environment that they've taken care of for thousands of years. They were doing this and then we came along and did our own thing. Anyway.
It's a bit of a personal question, but I also have a TikTok, and like when I read that comment in the top corner that you highlighted, that was like absolutely heartbreaking. How do you deal with that?
Well, I started talking about this in 2018. And the first comments that came through there were very confronting. But having talked about it for as long as I have now, I'm very much have quite a wall to it. But there are a lot of positive comments to this. There was a lot of support as well. Particularly, there was a lot of support from teachers saying they were going to take an effort in their classroom to do that, which if there's one of those comments and 100 of those, I'll take it. That's still great. Yeah, it's definitely hard, and some days are harder than others, but on the whole, most of them are fairly ridiculous. Like I laugh because there's so many of feminist blah, 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 feminist blarney, oh, this is just a feminist agenda. Yes, that's quite literally the point. So a lot of the comments are entertaining in that way. I had the best roast ever, and then the guy deleted his comment because he clearly couldn't handle the heat. Commented something like, in my research, I've not seen this, it's not a thing. And I was like, can you point to a peer-reviewed paper? Because we have a peer-reviewed paper now. And then he deleted his comment. So evidently doesn't have the peer-reviewed paper. So sometimes it can be entertaining, but also I think I've learned the ones like this, you're never going to get on side. But what you can do is use these ones to get the people who are on the fence on your side, to show that sort of stuff and that rhetoric that's on the other side and how absolutely ridiculous and horrible it is, to show our side as being far more realistic, far more accessible and welcoming and just reasonable. So yeah, in that sense, they're also useful, but you do have to pick your battles because none of these people are ever going to be on the side of this stuff. Yeah.
How does the tertiary sector stack up?
It's very hard to say because there's no national regulation like the Australian curriculum. So even though we looked at individual states, they are all based on the Australian curriculum, and they've just sort of taken it, expanded it in the way that they want to. There is no such thing in tertiary education. And beyond that, courses as well, you may have one person design the course and then they're off because academic life. So yeah.
I mean, in terms of first year physics, for example, there's only really 3 textbooks in use.
Yeah.
So it could still be done.
That's true. Yeah, textbook wise, absolutely. But I think, yes, there are textbooks there. I don't know that uni students use textbooks to the same extent that high school students do. I think you're much more reliant on the lecture notes, the lecturer themselves and the slides. And unless you have a lecturer who's been made aware of this and put in a conscious effort to change that, which again, we can all agree, teaching isn't even necessarily the focus of the job of academics who have no experience teaching. It's already enough going on, let alone then also teaching this sort of stuff and taking that initiative can be really hard. And then you're probably gone, 3 years later. So yeah.
So my high school education in Japan, so I'm not aware of the Australian system, but what fraction of high schools actually follow the syllabus? Because in Japan, like third schools and final schools are not even.
No, it's the vast majority will follow the curriculum, especially in year 11 and year 12. It's very much taught dot point by dot point. They just go through because there's a generally either a statewide or national-wide sort of conglomerate, all everything together, assessment at the end of the year. And so they have to, because it's not school-based assessment at the end of the year, they have to be able to say, this is exactly what we're testing you on. This is exactly what we're going to teach you on. So if it's not in the curriculum, teachers just don't teach it. It's not happening, which is why, yes, we can look at the textbooks or yes, we can look at what teachers are teaching, but unless you have a teacher who has extra time and money to do that, it's probably not going to happen. And if it's not in the curriculum, it's not going to happen either. It's very curriculum focused, year 11, year 12, pretty much all schools, yeah.
So can I ask a follow-up to that? Because the caveat is the International Baccalaureate.
Yes, yeah.
Have you looked at IB and how?
No, haven't looked at that one. Maybe one day, hopefully. But yeah, just the cool one.
It's quite Eurocentric, but I imagine still from a gender perspective, it would be rubbish. I would be very confident in saying it's not going to be good. Yes, yeah, yes.
Would you even be able to have influence on the IB curriculum?
Oh, no one can influence IB.
Yeah.
No, but highlighting it is the first step.
As a comparison.
As a comparison. Yeah.
And that was also, even though we were already working with New South Wales and working with Queensland as well on the curriculum development and improvement, we still wanted to publish this and have it out so that any improvements we do have, we can actually see the statistical improvement, but also compare the enrolment numbers, see if it is making a difference. There are over 300 initiatives around Australia to increase the representation of women in STEM, and we are seeing next to no progress as a result of that. Largely, we can't tell which ones are good because there is just no evaluation data. There is nothing. I've very much had to come to this sort of stark realization myself, was now that we're registered as a not-for-profit and in that sort of space, the number of not-for-profits out there working on increasing gender representation, that is just a big corporation dumping a whole bunch of money that's now tax deductible to run a program for 3 years that says, we saw this many thousands of students for 1 hour and then we fucked off and we didn't do anything else. That is the vast majority of the programs that are out there, and they just don't work. They don't do anything. And so, yeah, having this, hopefully we can actually start to see, does it make an improvement? I honestly don't know that it will. It's certainly not going to solve everything. Certainly putting the names on is just a band-aid solution to a very complicated problem. Changing the entire pedagogy and the approach to teaching science, I think, is far more useful. It may have a larger impact, but it's a lot harder work. But we won't know if it's going to do any good unless we try it. We know that this isn't working. To continue to do the same thing over and over and expect a different result is bad science. So why would we do the same in science education? We're not going to see an improvement in representation if we continue to teach stuff like this. So.